The next talk will be given by José Figueroa. He will talk us about slowly rotating black holes modeled by Solv geometries.
Thank you. Hi, first of all, I want to thank the organizer for the opportunity of presenting here. I'm going to talk to you about a new slowly rotating solution modeled by the Solv geometry that was found as a part of a work in progress in collaboration with Julio Oliva and Marcelo Yarzo. Well, first, I want to recall that the black hole solution. I want to recall the black hole solution with the, negative lambda in general relativity. Then I will talk about the black hole with Thurston geometries, and then about the construction of the slowly rotating black hole. And finally, I will talk about the conclusion and work in progress. We have the Schwarzschild ADS solution, its rotating generalization, the curved black hole. In 3 dimensions, we have the VTC black hole, and in high dimension, we know that we have also rotating solutions. All these black holes share the same asymptotic behavior. They are all asymptotically ADS. Also, to have a well-defined evolution of the system, we must impose a appropriate boundary condition at the boundary, accommodating this solution. To do that, there are 3 important requirements that the boundary condition must satisfy. First, they should contain the physically relevant solutions, as it is the rotating black hole. Also, they should be invariant under the symmetry group of the vacuum. And finally, they should make the surface integral finite. With these 3 requirements, Genoa and his collaborator proposed a boundary condition for spaces that are asymptotically ADS in arbitrary dimension. That are the following boundary conditions, and satisfy these 3 requirements. Okay. Then with the boundary condition at hand, one can ask about the asymptotic symmetries of this boundary condition, namely about the symmetry of this boundary condition. Namely the asymptotic symmetries. In 3 dimensions, something interesting happened. The algebra of asymptotic symmetries is infinite dimensional and corresponds to 2 copies of the Witt algebra, the same algebra of symmetries of a 2D CFT. Also, the corresponding charge acquires a central extension. This allows to reproduce the Bekenstein-Hawking entropy of the VTC black hole by counting microstate using the Carter formula. I find this remarkable. In contrast, in higher dimension, the asymptotic symmetry is just the group of isommetry of the vacuum. And as it is a semi-simple algebra, it does not admit non-trivial central extensions, as the Witt algebra in the d equal 3 case. With this in mind, we decide to study another sector of general relativity in 5 dimensions, found first by Kadriou and Woolgar. They found black holes with horizon modeled by the Thurston geometries. These are 8 homogeneous geometry that are considered as a kind of building blocks of the 3-dimensional Euclidean spaces. One of the solution they found is the Soly Black hole that I will present now. Okay. This is the metric of the black hole modeled by the Solv geometry, where mu is an interaction constant related to the mass of the spacetime. When mu is equal to 0, one finds a kind of vacuum for this sector of the theory that is a different sector of the asymptotically ADS space, because here at infinity one does not record the ADS space. It's interesting it is remarkable that this is a solution of the general relativity without matter. That's it. Okay. when mu is equal to 0, the isometries are the following. We have 5 Killing vectors that satisfy this solvable algebra, and when mu is different from 0, so when we have mass, this vector is broken. This 2. Note that this algebra is not semi-simple. It has an abelian ideal given by these 3 vectors. So it might require a non-trivial central extension, and that is an important motivation of our work. Then, with this in mind, and the natural question arises: which are the asymptotic conditions that permit to accommodate these general relativity solutions? Which are the asymptotic symmetry algebra of this boundary condition, and if could have a central extension or not, and is there a rotating generalization of this black hole? And this last question is related to the first one, because one can use the rotating black hole to constrain the boundary condition in some way, as I will explain now. So we want the rotating solution to be part of the phase space, and also we want that the asymptotic symmetry group of the vacuum is included in the asymptotic symmetry group of the theory. So, this can restrict us. This can tell us how much restrictive our boundary condition can be. To do this, we act with all the generation of the background isometry group on the rotating black hole. And from this new metric, we read of the deviation from the background. And this will correspond to the most restrictive falloff we can impose. Interestingly, this can be done also with the slowly rotating curved black hole instead of the full curved black hole. So, with this in mind, we know, and in order to explore the phase space and asymptotic symmetry group of this sector of the theory, we search for slowly rotating black holes with modeled by Solv geometries. And for that, we propose the following answer, given here. This corresponds to a perturbation of the black hole presented before. Then we obtain at first order in the perturbation parameters. We found 2 equations for the function f and g, and the separation constant c. We can solve this equation, finding that g can be solved in terms of exponentials, and f in terms of a hypergeometric function. One branch of the f function that depends on r have to be discarded because it modifies the asymptotic behaviors. So one does not approach to the black hole with mu equals 0 at infinity. And the branch and the other branch goes to zero at infinity if we have the following constraint on the separation constant. Finally, we find this solution for the f function, where this corresponds to an hypergeometric function. In order to impose further constraint and study if it was indeed a rotating solution or not, we compute the charge of the solution using the covariant phase space formalism that give us the variation of the charge integrating a two form. In general relativity, the expression of the two form was computed before and is given by this, where h corresponds to the perturbation on the solution. And using this, we found the following charge. And the charge corresponding to the angular momentum in the coordinate x and y, one can analyze the integral of this charge and and see that one has to impose a constraint on the separation constant in order to the charge not diverge. I'm sorry. And the constraint is the following. Now we can take two cases. If c squared is strictly less than 1, both charges will vanish, and the solution will correspond to a linear hair on the black hole background. Instead, for c squared equal 1, both charges receive a non-vanishing contribution to the surface integrals.
5 more minutes.
Okay. In this case, in order to avoid the divergences in the z direction, we kill one of the integration constants of the g function, and we finally have this metric for the rotating black hole. It is a simple metric compared to the non-rotating black hole. And finally, we obtain the following chart. This corresponds to the mass, and this to the angular momentum in the two direction x and y, and are non-vanishing. Finally, the conclusion. We constructed a new slowly rotating solution and a solution with a linear gravitational hair. This in order to propose appropriately boundary condition for this sector of the theory and to study its symmetries. We are working on that currently. Also, it will be interesting to explore, and we are currently exploring that, if this can be extended for the neat black hole, that is another of the 8 Thurston geometries. Also, one can wonder if the slowly rotating black hole that we found can be extended to a fully nonlinear one. I think this will be a third work, but it is a natural question also. Also, there is still much to do to understand those black holes modeled by the Thurston geometry. One interesting thing is the asymptotic region that of the Solv black hole can be thought as a generalization of Lifshitz, and it's well known that this geometry, the Lifshitz geometries, appear in non-relativistic holography. And there is a couple of work on that by some professor of La Plata, I think. Also, one can wonder what is the interpretation of this configuration in the Kaluza-Klein reduced theory, because we have two directions, the x and y direction, in which we can compactify, and finally, if this solution can be embedded in supergravity. And that's it. Thank you for your attention. I'm sorry for my English.
Okay, thank you, Jose,
Okay.
for your talk. Are there any questions for Jose? Questions? Well, I have a question.
Okay.
Well, you started motivating this construction of solutions from asymptotic symmetries, and at the end I saw that you computed the charges, but I also noted that those charges, you kept the delta because they were not integrated. There was an epsilon factor times delta, some parameter reaction.
Yep. Yes.
Yes, but then you chose this constraint to make them finite, at least, or not divergent. But so then you got some other charges, I think, some next slide. Okay. And my question is, because I can see there that they are not integrated, and I would like to know if you are.
Oh, yes, they are integrable. One can see here easily that the charge associated with the angular momentum in the x direction is just a times the other factor. One can integrate.
So you are taking Epsilon is a constant.
Yes, it's a constant. See, I'm sorry. I should write the integrate the charts integrated.
Yes, because they are integrated. So I was confused whether they were somehow dependent on the angles because you kept this volume.
Okay, no. Epsilon is a constant.
And then they, if they were somehow dependent on the coordinates, or they are constants.
No. Epsilon is constant, and so it is A.
Okay.
So they are integral. I should write it. I should have write it integrated instead of liberated. Thank you for your question.
And I don't know if you looked for an algebra of the charges, some canonical algebra at the end.
We are working on that. We are having some trouble, but
yes,
it is work in progress.
Perfect.